I'm glad to be here. So yeah, I'm gonna talk a little bit about some exciting high redshift cluster stuff we can do in the next decade with Axis. So let me just get started. So here's just a picture of the Chandra X-ray Observatory. This is one of the most famous images that Chandra has taken of the Perseus cluster. If we look out to about redshift 0.6, 0.7, this is what clusters look like to Chandra. You can still see a lot of structure, and we go out to redshift 1.5, and we start to really lose a lot of the information, but we can still do science there, which has been a lot of fun. So let me just start with a brief overview of what is a galaxy cluster. So these are collections of hundreds to thousands of galaxies, all mutually bound by gravity. The galaxies are sort of inconsequential for the most part. They're 1% of the total mass, and they're sort of like test particles in this fluid. The dominant baryonic component is this intracluster plasma, which glows in the X-rays, and this is why we want X-ray telescopes to point at clusters. And this is roughly 10% of the mass, and the remaining 90% or so is dark matter, as we know. And so clusters in the nearby universe are remarkably similar from cluster to cluster, and that's really what makes them great cosmological probes. And so when we look out at galaxy clusters, we see that basically every cluster has a single giant elliptical at its center. We call that the brightest cluster galaxy. Basically every cluster we look at has, every brightest cluster galaxy is radio loud. It has radio jets, and these radio jets are doing work on the intracluster plasma and preventing it from cooling. This is a so-called cooling flow problem. So wherever we look, we see this nice correlation between the jets from that central massive galaxy and the cooling rate of the hot intracluster gas. Wherever we look, we see the same gas fractions in clusters. So the fraction of the total mass in this intracluster plasma is about the cosmological fraction. We see the same metallicity in the intracluster plasma from cluster to cluster. It's always a third solar wherever we look. And we see the same entropy, pressure, temperature, density profiles. The hot intracluster gas is just very similar from cluster to cluster. And again, that's why we can use these as cosmological probes. But we're not really sure when they became, so regular, and when all of these, regular properties were established, right? So we don't know when the central cluster galaxy landed in the center of the cluster. Did it, migrate there, or was it, did the cluster form around it? We don't know when the metals were deposited in the intracluster plasma. We don't know when clusters started to cool, and when that cooling when that feedback response from black holes came online. We don't know when the intracluster plasma was established, or when clusters, separated from the protocluster web, although that is, pretty well handled by simulations. And so, the timeline of cluster evolution, I've put these things on a timeline, but these are all guesses. And so we really don't know a lot about how clusters that are so regular at redshift 0 came to be. So why don't we have all the answers yet? It's mostly because we've been limited in our samples to X-ray selected samples. And so here's a picture of clusters selected with the Rosat All Sky survey, the initial survey, and then the MAX and EMAX. Well, I don't think EMAX is on here, but the MAX follow-up. And so the red points here are Rosat selected clusters. And you can see that, we're sensitive to the highest mass clusters at higher redshift. And really, we'd like to be sensitive to clusters, down here at high redshift. This is where we expect clusters to grow with time. They should increase their mass with time. And so we're sort of selecting against that evolutionary trend. And so it's hard to find high redshift clusters. That's half of the problem. But even though we are recently starting to find these high redshift clusters, the other half of the problem is it's hard to follow them up. And so here's a picture of the El Gordo cluster. This is the most massive cluster in the universe. I just picked this one because it has a lot of counts, and it is small on the sky, so it's easy to do these little mocks of. So if we subsample the El Gordo cluster to what it would look like as a progenitor at really high redshift, you have the picture on the right. And so this is on the right is what we can achieve for redshift like 1.5 clusters. And so it's really, really difficult to see what's going on in that system. You can maybe see that there's an overdensity of counts here and maybe an extension in this direction. And so for comparison, if you take the Perseus cluster and you put it at redshift 1 and you lower its mass, so it's now the progenitor of the Perseus cluster, you expect about 2 photons per hour from Chandra. And so these are just really expensive observations to follow up these high redshift clusters. And so this is what we do at intermediate redshift, and this is what we've been able to do at the highest redshifts. 100 counts is kind of our target typically. So we've solved sort of the first problem, the problem of not having high redshift clusters to study by going to Sunyaev Zel'dovich surveys. So I'm not really going to go into this at all today, but we can find clusters based on the shadows they cast on the microwave background, and that's a redshift independent selection. So here's a plot of mass versus redshift. These are cluster samples, the blue points here are the ROSAT selection. The black and green points are South Pole Telescope selected cluster samples. And so we see clusters up to, redshift 1.5 in these surveys. And so over the past decade, about 1,000 new clusters have been found by the South Pole Telescope. The Atacama Cosmology Telescope and Planck telescopes have also found, similar numbers of clusters. And so we're really, in a large sample regime now in terms of high redshift clusters. It's just really expensive to follow them up in the X-ray, but we've still been trying. And so this rectangle basically represents our follow-up. So most of the black and green points in this rectangle have Chandra data from the past 11 cycles. We've gotten about 8 megaseconds to follow up these clusters. And there's about 150 clusters that we followed up in this region. And so this sort of represents the best we can do right now on studying high redshift clusters in the X-ray. So what have we done with that? I'm not going to dwell too long on this because the point of this talk is to look forward, but let me just tell you sort of what the state of the art is right now. And so, we've been able to probe how well heating AGN feedback can prevent runaway cooling of the intracluster medium. And so this is work that Florian Ruppin published this year. So this is the heating cooling balance in the centers of clusters as a function of redshift. And out to about redshift 1.2, we don't see any evolution. And so feedback has been working hard in the centers of clusters for at least the past 9 million years. We can look at the metallicity of the intracluster plasma. And so this is work led by Anthony Flores at Stanford University with Steve Allen. As far back as we look, clusters have the same metallicity, about 1/3 solar metallicity. So Anthony finds a little bit less than 1/3 solar, but it's consistent at the 1 sigma level with 1/3 solar. So no real evolution in the metallicity of clusters out to about redshift 1.5. And then finally, we can look at the morphology of clusters in the X-ray. The morphology should be indicative of the dynamical state. And so if 2 clusters collide, then the morphology is highly asymmetric. And we find very little evolution in the fraction of clusters that look like they've undergone a recent merger. And this is partially due to the fact that at high redshift clusters actually relax faster. And so we have to take that into account. And so we were able to probe the sort of dynamical state of clusters as well out to redshift 1.5. So if you're sort of paying attention, you'll see that our limit in all these studies is really between redshift 1 and 1.5, right? And so we're starting to learn a lot about the intracluster medium and the galaxies and the AGN and clusters at higher redshift, but we're really still capped out at about a redshift 1.5. And this is only partially due to selection, samples. Really it's driven by the fact that we're hitting a wall with Chandra. As clusters are at higher redshift, they're fainter. Surface brightness goes like 1 + e⁴, right? And so you really get hit as you put these clusters further away, but they're also redshifted into softer bands where Chandra is losing sensitivity every year. And so we're really, it's not a matter of just, trying harder at this. We're really hitting, a fundamental limit. So what does the future hold? Well, it holds, excitement, I think. So here's on the left is this nice table made by Rangunathan in 2000, this year, that basically, shows what all these upcoming millimeter wave surveys are going to find over the next couple decades. And so with the original South Pole Telescope survey, we're in the hundreds of clusters regime. 10 years later, in a couple years, we're going to publish the SPT3G survey, and then we'll be in the thousands of clusters regime, with hundreds of clusters above redshift 1.5. And then 10 years after that, give or take, CMBS4 will be producing cluster catalogs with tens of thousands of clusters and thousands of clusters above redshift 2. And so we're really going to be in a large sample situation, imminently. And these higher redshifts are exciting because, really we've been sensitive to what's going on down here, less than redshift 1.5, where the universe is really settling down, right? The star formation rate is diving with decreasing redshift. The black hole accretion rate is diving with decreasing redshift. So we've been probing cluster and galaxy evolution, in this blue band. With AXIS, we're going to be at the peak, the most exciting time of the universe in terms of galaxy growth, in terms of black hole accretion, and in terms of cluster formation. We think this is around when the ICM, really virialized and relaxed in clusters. And so we're going to be in the 100,000 cluster regime at the launch of AXIS, with really no ability to follow up, the cores of these clusters and these systems in detail. So just check my time here. I think I'm doing okay. So these are the three things that I think are exciting with high redshift clusters in the era of AXIS. This is by no means an exhaustive list. But it's these are the questions I'd love to ask before I retire, basically. And so, I'd love to know, when the intracluster medium turned on in the X-ray, basically. When did the potentials of clusters get deep enough and the, accretion of gas, substantial enough so that you saw these clusters light up in the X-ray. And so we know there's protoclusters out to redshift 6 or further, but certainly they're not deep enough potentials to sort of ignite the X-rays. And so I think something like AXIS can really answer the question, when was the intracluster plasma established? Connected to that, we'd love to know when it was enriched. The metals we see in clusters today probably came from winds in galaxies early on. Early processing probably around redshift 3, but that's really a guess, or a model dependent guess. And so we'd love to know how this enrichment happened and when it happened. And then finally, personally, I'm most interested in how did or when did AGN feedback turn on? At what point were these radio jets sufficient in energy and in reach to prevent runaway cooling of the ICM? And so these AGN sort of act as cosmic thermostats, but I'd love to know the properties of those thermostats and when they really turned on. So I'm just gonna use the final few minutes to really dig into these two things, which are things that are easier to sort of simulate and to understand what can AXIS do for us here, and what kind of AXIS do we need to achieve these science goals. And so I'm going to dig a little bit into these. And this is with a lot of help from Steve Allen and Anthony Flores at Stanford, who basically did the enrichment side, and I did the AGN feedback side. So first, this is basically a summary plot of like what we know about the evolution of the metallicity of the intracluster plasma. And so this is anchored at redshift 0 with deep Suzaku observations of 11 clusters. This one is Perseus. These are 10 other clusters a little further away than Perseus. And so that gives us a really good handle on this idea that, the ICM is a third solar metallicity, no matter where we look. We looked at about 100 clusters between redshift, 0.3 and 1.2. This is work I published in 2016, and we found no evolution in the metallicity of the intracluster plasma over that range. This was using a combination of Chandra and XMM and Suzaku data, actually. And then most recently, Anthony Flores has really pushed into the high redshift regime using Chandra and XMM, and has found tentative decrease in the metallicity at about redshift 1.3. And so if you model all of these data points, which Anthony did, this blue band is basically our prediction for what the metallicity ought to be between redshift 1.5 and 3. And so this blue band is not very well constrained because we don't have a lot of data at high redshift. And so it's consistent with a no evolution scenario, but it's also consistent with the predictions from illustrious TNG. And so illustrious TNG predicts that about half of the metals, were made between, redshift 3.5 and 1.5. And so, the goal here is to get this blue band smaller so that we can start ruling out models and start understanding the physics behind enrichment. And so constraining this evolution tells us things about galactic winds, how effectively metals are moved out of galaxy halos and into the more diffuse intracluster halos or into cosmic filaments, and really how all this metal transport happened. And so Steve and Anthony did these really nice simulations of what we can expect with about 4 megaseconds of axis on the highest redshift clusters, and this is what we expect to see. And so, with 4 megaseconds of axis observations on these high redshift clusters, we're basically looking at similar constraints to what we have on systems like Perseus and these nearby Suzaku observations, but at redshift 2, 2.5, 3. And so these, I've taken some liberty with Anthony's points here. These are the right error bars, but they're not the metallicities he simulated. I just put them onto this line for illustrative purposes. But the point is that we're looking at uncertainties in the average metallicity that are similar to what we see, in the nearby universe now. And so we can really differentiate between different models of pre-enrichment or early enrichment or late enrichment or no evolution, right? And so these types of observations will really go a long way there. So these are the figures that actually Anthony did produce that I've been alluding to, and the important thing here is that to study the evolution of the intercluster medium, the metallicity specifically, we really need soft sensitivity, because these high redshift clusters, all the information is in the soft X-rays, and we're shifting that by factors of 3 or 4 between redshifts 2 and 3, and so you really lose a lot of the flux and a lot of the information as you give up soft X-ray sensitivity. And so Anthony compared, what if we have a 0.3 keV cutoff to a 0.5 keV cutoff? And the gist is that you lose about 80% of the flux within R500 if you give up those 0.2 keV. And so clusters they appear very, very soft at these high redshifts. And this is only a redshift 2 system. If you put that at redshift 4, or redshift 3, it's shifted even redder, obviously. And so this is the case for a very soft sensitive mission. So the other thing that I'm excited about is understanding the evolution of AGN feedback, or the initial onset of AGN feedback. So this is the poster child for AGN feedback in clusters. It's MS0735. The blue is the X-ray plasma. The red are radio jets, and you can see that the radio jets appear to be punching holes or blowing bubbles in the hot gas, and so you can see these bubbles in the hot gas over here. And so we'd love to be able to see this out to very high redshift. Right now we're limited to about redshift 0.5 seeing systems like this. And so I did some quick mocks of what would a system like Zwicky 2701, which has these bright or these high contrast bubbles close into the center, what would that look like at different redshifts? And so this is just the cluster itself. at redshift 0.5, 1, 1.5, and 2 with Chandra and axis. And you can see that the clusters, apparent out to high redshift with axis much longer than with Chandra. And this is only 100 kilosecond exposure. And then if we subtract off the model emission, then we can see these bubbles in the clusters simulated with axis, where we lose them at about redshift 0.5 with Chandra. These are pretty idealized simulations, so I then went and did a much more careful job of things and produced a much more complicated plot. And so let me just walk you through this really quick. So on the left, these are I sort of simulated two types of feedback outbursts. A really rare, 1 in 100 cluster outburst is on the left. So this is basically as big as it gets. So something sort of like this here. And on the right is a more typical system. So, basically the median cool core cluster, and so what we expect in the ensemble clusters. And so for each of these plots, you can see on the y-axis, I'm showing the limiting redshift. So how far out can we see bubbles in this scenario as a function of the PSF of our X-ray telescope. And so for the biggest bubbles, we're confusion limited at PSFs worse than about 3 arc seconds full width half maximum. And so so that means that if you want to see these most extreme bubbles, you want better than 3 arc second full width half maximum, or it doesn't really matter how much exposure time you're putting into it. Basically, above better than 3 arc second full width half maximum, it matters how much exposure time you spend, because you're not confusion limited anymore. And so you can see that, if you put a half megasecond into, a cluster at redshift 1.7, you'll detect these bubbles at 5 sigma. And that's really, redshift 1.7 is around, or redshift 1.8 is where we expect radio mode AGN evolution to peak, or strong radio AGN evolution, I should say. If we consider a more typical case, then bubbles now are smaller. If there's less jet power, they're probably closer in, or we wouldn't really be able to see them as well. And so your confusion limit moves inward. And so for a typical cluster at high redshift, we expect the confusion limit to be at about a 1.5 arc second full width half max. And so if you want to see bubbles in an average cluster, then you really need arc second or better PSF. And so both of these plots show that with a substantial investment of exposure time and adequate PSF, we can detect this AGN feedback out to basically the peak of AGN feedback, as shown by Merloni and Heinz. And so, really the important takeaway here is that this confusion limit, if you want to see these bubbles, it's important to go deep. It's important to have soft sensitivity, but it is absolutely critical to have high angular resolution, or everything else is wasted. All right, so I think I'm basically at a time here. So let me just wrap up with these 3 points again. So, I think the really exciting opportunities with Axis combined with the cluster samples we expect in around 2030, in the 2030s, are the detection of the sort of primordial intracluster medium, or the proto intracluster medium. And really we need low background and soft sensitivity to do that. It'd be really great to detect the early enrichment of the ICM and to understand how did metals get deposited into the hot diffuse universe. And for that we really need effective area at down to a third keV. And then finally, if we'd like to understand, when AGN feedback became important in the most massive halos, and that is where AGN feedback seems to be doing the most work, right, is in the most massive halos. then we really need, the angular resolution is critical, and the soft sensitivity is super important. So I'll stop there and take any questions.
Yeah, so great talk. So if people have questions, you can put them in Slack as well, in the chat, or just raise your hand and we can take a few questions here. Franz, you want to go ahead?
Sure. So, Michael, how are you going to detect or know that the Redshift 3, Redshift 2 clusters are there to begin with? Where does that come from?
Right. So the samples, in the era of Axis are going to come from these, in my opinion, from these millimeter wave surveys. And so, in the next couple of years, we'll publish the SPT3G catalog, which will find roughly 500 clusters above Redshift 1.5, close to 100 clusters above Redshift 2. More in line with Axis maybe is CMBS4, which will be finding thousands and thousands of clusters at these redshifts. And so, I don't look at Axis as being a cluster finder. I think these millimeter wave experiments have shown that they're just phenomenal at finding these high redshift clusters. The problem is that clusters are point sources to the millimeter wave surveys, and so we get exactly one piece of information, which is the mass, and we don't know anything about how that mass is distributed or the properties of the plasma. We just have an integrated measurement of the plasma pressure.
Okay, so the plan is like to do there's an intermediate stage where you go and you say, okay, it actually has X-rays. And then you say, okay, then we want to actually pump 4 million megaseconds into it to get the mass.
No, it almost has to have X-rays, right? So if we detect detected in these millimeter wave surveys, what that is saying is that there is a megaparsec column of plasma, and as long as we're restricting ourselves to high signal to noise detections in these surveys, there's basically no false detections. So we followed up 150 SPT selected clusters with Chandra, and we have no false detections.
Okay, great.